Right now, volcanic headlines are arriving from almost every direction. Etna has returned to eruptive activity at its summit. Sheveluch in Kamchatka recently blasted ash to aviation levels and briefly forced the highest color code. Indonesia has multiple volcanoes producing ash, lava, or elevated seismicity. Mayon in the Philippines is still in an eruptive period, even though its alert level was lowered in early August. And in Hawaii, Kīlauea is sitting between spectacular lava fountaining episodes, with scientists expecting another episode in the coming days. Put those stories side by side and the pattern looks unsettling. Volcanoes appear to be waking up everywhere at once. But is that really what the data show? Or are we watching a normal amount of global volcanism compressed into an unusually visible news cycle? Today, we are going to separate the signal from the noise, look at the volcanoes making headlines, examine the global statistics, and ask the question that matters most. Is there any evidence that Earth's volcanic system is entering a new phase? Start with the number that makes the current moment look dramatic. In the Smithsonian Institution and U.S. Geological Survey Weekly Volcanic Activity Report, covering July 30th through August 5th, 2026, 23 volcanoes appeared in the report. 5 were listed under new eruptive activity: Etna in Italy, Fuego in Guatemala, Krakatau in Indonesia, Puracé in Colombia, and Tellica in Nicaragua. The same report also included continuing eruptive activity at places such as Sakurajima in Japan, Dukono and Ibu in Indonesia, Great Sitkin in Alaska, Kīlauea in Hawaii, Mayon in the Philippines, Reventador and Sangay in Ecuador, Semeru in Indonesia, and Sheveluch in Russia. Sinabung was listed for continuing unrest. 23 names in a single report is enough to create a very convincing global map full of red dots. But that map needs context immediately. The Smithsonian's weekly report is not a census of every volcano erupting on Earth, and it is not designed to measure a weekly global trend. The program says the report averages roughly 16 to 17 volcanoes and intentionally highlights activity that meets specific reporting criteria. Volcanoes with routine, nearly continuous activity can be omitted during weeks when nothing meaningfully changes. Submarine eruptions can be missed because observations are sparse. Some observatories report daily, others weekly, and some remote volcanoes may be recognized only after satellite imagery is reviewed. So 23 reported volcanoes is an attention-grabbing week, but it is not the same as 23 volcanoes suddenly starting from zero. That distinction is the first key to this entire story. The Global Volcanism Program counted 40 volcanoes in continuing eruption status as of its March 31st, 2026 database update. It says that 40 to 50 continuing eruptions at any given time is typical, with around 20 volcanoes generally erupting on a particular day. Looking across the year since 2000, the Smithsonian reports an average of about 78 total eruptions per year when ongoing eruptions are included, with the annual total usually falling in a broad range from the mid-60s into the high 80s. In other words, Earth is not normally quiet. Our mental picture of a calm planet interrupted by occasional volcanic emergencies is wrong. The background state of Earth includes dozens of active volcanic systems all the time. Now look again at the current headlines. Etna is a good example of why one week can suddenly feel different. During the latest completed weekly reporting period, Italy's Etna showed summit activity that included explosions, ash emissions, strombolian bursts, and lava effusion. Etna is one of the most closely observed volcanoes in the world. A change at its summit can be seen rapidly by webcams, thermal cameras, satellites, seismic networks, and observers on Sicily. That visibility means an eruptive pulse can appear across social media within minutes, even when the event fits a long history of recurring activity at one of Europe's most persistent volcanic systems. Then there is Sheveluch in Kamchatka. During the same week, explosive activity sent ash as high as roughly 10 kilometers above sea level on July 31st. The aviation color code was temporarily raised to red, the highest level, before being lowered again after the major explosion stopped. The ash plume traveled thousands of kilometers across the North Pacific region. That is objectively significant volcanic activity, especially for aviation. But Sheveluch is not a volcano that suddenly became active in 2026. Its current long-lived eruptive period has roots going back decades. The dramatic ash cloud was a powerful event inside an already active system. not evidence that a previously dormant part of the planet abruptly switched on. Mayon tells a different story. The Philippine volcano began its current eruptive period in January 2026. By late July and early August, observatories were still detecting volcanic earthquakes, rock falls, gas emissions, and lava flows in several drainages, but the intensity had decreased enough that PVolcs lowered the alert level from 3 to 2 on August 5th. That matters because the same week that global headlines can be assembled to suggest accelerating unrest, one closely monitored volcano was actually moving in the opposite direction. Activity was still above background, hazards remained inside the permanent danger zone, but the trend was toward reduced unrest rather than escalation. Kīlauea adds another layer. Its current summit eruption began in December 2024 and has evolved into a remarkable sequence of episodic lava fountaining events separated by pauses. By early August 2026, 52 fountain episodes had already occurred. After episode 52 ended on July 28th and 29th, the summit entered another pause while the shallow magma system repressurized. On August 11th, the Hawaiian Volcano Observatory said Kīlauea was not erupting at that moment, but models indicated another episode was likely between August 13 and 17. So a headline saying Kīlauea is showing renewed unrest is accurate. Yet the deeper story is a repeating cycle that scientists have been following for many months. Indonesia is where the global map can look most intimidating. Dukono, Ibu, Lewotobi Laki-Laki, Lewotolak, Merapi, Semeru, Krakatau, and Sinabung all appeared in the latest weekly report in one form or another, but Indonesia sits across one of the most volcanically productive plate boundary systems on Earth. The Australian and Indo-Australian plates interact with the Sunda and other regional plates, generating long arcs of subduction zone volcanoes. When several Indonesian volcanoes are active at the same time, it is visually striking. But it is also consistent with the tectonic architecture of the region. These volcanoes are not sharing one magma chamber. They are separate systems responding to local magma supply, local crustal structure, local gas pressure, and local stress conditions. This brings us to the second key idea. Geography creates the illusion of synchronization. Most of the world's active volcanoes occur along plate boundaries, especially around the Pacific Ring of Fire. Subduction zones produce chains of volcanoes because one tectonic plate descends beneath another, releasing water and other volatiles into the mantle above the slab. That lowers the melting temperature of mantle rock and helps generate magma. The magma then rises through the crust, sometimes collecting in reservoirs before moving toward the surface. Because one subduction zone can extend for hundreds or thousands of kilometers, many volcanoes can occupy the same broad tectonic belt without being directly connected to one another. Think about the Ring of Fire as a series of neighborhoods built along the same kind of geological infrastructure, not as a single electrical sea. Our circuit. A volcano in Japan, a volcano in the Philippines, one in Indonesia, one in Kamchatka, and one in the Aleutians, may all owe their existence to subduction. But an eruption at one does not send magma racing through an underground pipe to the others. The distances are enormous, the magma reservoirs are local, and the timescales of magma generation and ascent differ from volcano to volcano. What they share is tectonic setting, not a common trigger switch. Hotspot volcanoes show the same principle from a different direction. Kilauea and Mauna Loa in Hawaii are not part of a subduction arc. They sit above a mantle hotspot while the Pacific Plate moves overhead. Their magma supply reflects processes beneath Hawaii, not pressure being transmitted from Etna, Mayon, or Sheveluch. Iceland combines hotspot volcanism with a spreading plate boundary. East African volcanoes are influenced by continental rifting. The Andes are dominated by subduction. These are different engines operating inside the same planet. A global list can make them look coordinated when, geologically, they are often independent. So what exactly counts as volcanic unrest? Unrest does not mean eruption. Volcanologists use the term when a volcano departs from its established background behavior. That might mean an earthquake swarm beneath the summit, a change in the type or depth of earthquakes, measurable inflation of the ground, increasing sulfur dioxide or carbon dioxide emissions, a rise in thermal output, new fumaroles, changes in crater lakes, or tremor caused by moving magma or fluids. Any one signal can have multiple explanations. Scientists become more concerned when several independent data streams change together in a pattern consistent with magma moving toward the surface. The word background is crucial. Volcanoes are naturally noisy systems. Hydrothermal fluids circulate. Rocks crack. Gas escapes. Shallow magma can move without erupting. At a heavily monitored volcano, the normal baseline might include dozens of tiny earthquakes each week and persistent gas emissions. At another volcano, a sudden swarm of 10 earthquakes could be highly unusual. That is why raw counts from different volcanoes cannot simply be added together to create a meaningful global unrest index. 10 volcanic earthquakes at one system may mean less than one particular long-period event at another. Context is everything. Ground deformation is one of the most valuable clues. When magma or pressurized fluids accumulate at depth, they can push the surface outward or upward. GPS instruments can measure changes of millimeters. Tiltmeters can detect tiny changes in the slope of the ground. Satellite radar, known as INSAR, can compare repeated images and reveal broad zones of inflation or deflation. At Kīlauea, these deformation patterns are so well measured that scientists can track the recharge of the shallow summit magma system between fountaining episodes and estimate a time window for the next pulse. But deformation can also stop, reverse, or continue for months without an eruption. Seismicity is another major signal. Magma forcing its way through rock can generate brittle fracture earthquakes. Fluids moving through cracks can create long-period events or volcanic tremor. A migrating earthquake swarm can sometimes trace a dike intrusion as magma moves laterally or upward. But earthquake swarms do not guarantee an eruption. Some intrusions stall underground. Some volcanoes release pressure through gas without producing lava. Others erupt with surprisingly little seismic warning. Monitoring is about probabilities, not certainty. Gas measurements add another layer. Magma contains dissolved gases such as water vapor, carbon dioxide, and sulfur dioxide. As magma rises and pressure falls, those gases come out of solution, much like bubbles forming when a carbonated drink is opened. A change in sulfur dioxide flux can indicate that new magma is approaching the surface, but the interpretation depends on the volcano. Gas pathways can become blocked. Rain and hydrothermal systems can alter measurements. A decrease in gas can sometimes mean less magma is rising, but it can also mean gas is being trapped beneath a sealed conduit. Again, the local history determines what the signal means. Thermal cameras and satellites help fill the gaps. A new hotspot can reveal fresh lava, an expanding dome, a hotter crater lake, or increased fumarolic output. Modern satellites can repeatedly scan remote volcanic arcs that once might have gone weeks without direct observation. Ash clouds can be detected from space and tracked across flight routes. That improvement in observation has transformed our perception of global volcanism. Events that would once have remained local or completely unnoticed now appear on dashboards, automated feeds, aviation advisories, and social media almost immediately. This is one of the strongest explanations for why volcanic activity can seem to be increasing even when the geological rate is not. The Smithsonian's Global Volcanism Program has addressed this question directly and says it sees no evidence that volcanic activity is actually increasing. The historical record becomes more complete as populations expand, observatories improve, satellites become more capable, communications accelerate, and more remote regions receive monitoring. A graph of recorded eruptions through history therefore rises partly because our ability to detect and document them has risen. The record is not the same thing as the underlying reality. Imagine trying to compare the number of thunderstorms observed in 1850 with the number observed today. In 1850, huge portions of the ocean had no radar, no geostationary satellites, and no global network of automated weather stations. Today, almost every major storm can be tracked from formation to dissipation. A modern database would show far more observed storms, but that does not automatically mean the atmosphere suddenly began producing more storms. Volcano records have a similar problem. Better detection produces more complete counts, especially for small, remote, short-lived or submarine eruptions. That does not mean the current week is meaningless. The latest report really did contain multiple notable changes. Etna had new summit activity. Kīlauea produced ash plumes. Purake was reported with new eruptive activity. Sheveluch produced a high ash plume. Sinabung showed increased seismicity. Reventador continued at a high level. Those are real events. The scientific question is whether they form a statistically unusual global pattern that requires one common cause. Right now, the evidence says no. They are better understood as overlapping local and regional processes inside a planet where dozens of volcanic systems are active at any given time. This is where coincidence becomes a misleading word. If you flip a coin enough times, several heads in a row will eventually occur. If 40 to 50 volcanoes are in continuing eruption status, and more than 1,000 volcanoes have been active during the Holocene, some weeks will naturally contain several escalations, several declines, and several dramatic eruptions at the same time. The clustering can be real without being caused by a global trigger. Statisticians call this the difference between correlation and causation. The events overlap in time, but temporal overlap alone does not prove a connection. This is one of the most common theories after a major earthquake and a volcanic eruption occur close together in time. The real answer is nuanced. Large earthquakes can alter stress around nearby magma systems. Seismic waves from very large earthquakes can also travel around the planet and temporarily perturb distant volcanic or hydrothermal systems. Scientists have documented distant earthquake swarms and subtle changes after major earthquakes. Geological Survey notes that most tensions occurring shortly after a large distant earthquake happen by random chance, and compelling cases of direct triggering are rare. For an earthquake to trigger an eruption, the volcano generally has to be close to erupting already. A magma reservoir must already be pressurized, a conduit may already be near failure, or fluids may already be in a critical state. Passing seismic waves can provide a small nudge. They do not create a mature magma body from nothing in minutes. This is why the phrase chain reaction can be misleading. A magnitude 9 earthquake does not normally activate a planetary line of volcanoes, one after another. It may disturb sensitive systems, but each volcano still has to be independently prepared to respond. The same logic applies to claims about solar storms, planetary alignments, or mysterious pulses from Earth's core. Extraordinary claims need a mechanism and repeatable data. Volcanoes are driven primarily by plate tectonics, mantle melting, magma buoyancy, crustal stress, gas exsolution, and local plumbing systems. Researchers can measure earthquakes, deformation, gases, and heat. If a global external trigger were synchronizing eruptions, scientists would expect to see a reproducible statistical relationship that survives comparison against the enormous background level of normal activity. No such evidence currently explains the worldwide pattern in 2026. There are, however, slower global processes that can influence volcanism over long timescales. Changes in ice loading, for example, can alter crustal pressure in glaciated volcanic regions. After major ice sheets retreat, reduced pressure can affect magma production and eruption frequency over centuries to millennia. Sea level changes can also alter stresses on oceanic crust. These are legitimate areas of research, but they do not provide an explanation for a one-week cluster of volcanic headlines across Italy, Indonesia, Russia, Central America, Hawaii, and the Philippines. Another important distinction is the difference between eruption frequency and eruption magnitude. A planet can have many small eruptions without any increase in the probability of a giant eruption. Most volcanic events are modest by global standards. Small ash plumes, slow lava effusion, dome growth, and short phreatic explosions may be dangerous locally, but do not imply that a super-eruption is building somewhere else. The size of one eruption is controlled by the specific magma composition, volatile content, reservoir geometry, conduit conditions, and eruption history of that volcano. Explosive potential rises when magma is viscous and gas-rich. Silica-rich magma can trap gas more efficiently, allowing pressure to build before fragmentation. Basaltic magma, like much of the magma at Kīlauea, is usually less viscous and often erupts more effusively, though it can still produce powerful fountains and hazardous gas. Andesitic and dacitic systems in subduction zones can generate highly explosive eruptions, pyroclastic density currents, and widespread ash. That is why comparing volcanoes by a single global activity count can hide the differences that matter most for hazard. Ash is one of the most far-reaching volcanic hazards. Fine ash can rise kilometers into the atmosphere and travel hundreds or thousands of kilometers. It can reduce visibility, contaminate water, damage crops, irritate lungs, overload roofs when wet, and threaten jet engines. Sheveluch's recent high plume illustrates why aviation color codes can change rapidly, even when communities far from the volcano see little direct impact. The hazard footprint of an eruption depends not only on how much material is erupted, but also on wind direction, plume height, particle size, and atmospheric stability. Pyroclastic density currents are far more local, but vastly more destructive. These fast-moving mixtures of hot gas, ash, and volcanic fragments can race down valleys and across slopes at lethal temp. Aeratures and speeds. Dome-forming volcanoes such as Merapi can generate pyroclastic flows when unstable lava collapses. Mayon can produce pyroclastic density currents during more energetic phases. Because these hazards can occur with little time to react, permanent danger zones around active volcanoes are not arbitrary lines. They reflect the areas where past deposits and modeled flows show the highest risk. Lahars create another problem that can continue long after an eruption. Loose ash and volcanic debris can mix with heavy rain or meltwater and transform into concrete-like mud flows that move down river valleys. A volcano does not have to be explosively erupting at that moment for a lahar to become deadly. Tropical volcanoes are especially vulnerable during intense rainfall. This is one reason authorities may keep exclusion zones and river warnings in place, even when eruption intensity decreases. Volcanic gas can also be hazardous without a major explosion. Sulfur dioxide can irritate eyes and lungs and can form VOG or acid aerosols downwind. Carbon dioxide is heavier than air and can accumulate in low areas under certain conditions. Around Kīlauea, gas emissions remain an important concern, even during pauses in lava fountaining. At other volcanoes, changes in gas chemistry may give scientists clues about magma ascent. The same measurement that helps forecast activity can also be a direct public health warning. Now return to the apparent global spike. The strongest evidence against a planet-wide acceleration is the long-term baseline. The Smithsonian's current statistics show that 40 to 50 continuing eruptions are normal. About 20 volcanoes may be erupting on a given day, and the average total number of eruptions per year since 2000 is around 78 when ongoing eruptions are counted. The program's own answer to the question of whether volcanic activity is increasing is no. That does not mean every month is identical. Natural variability can produce busy weeks and quiet weeks. It means the long record does not support a sustained worldwide upward trend. The latest weekly report itself contains a clue. Several volcanoes listed as active have been erupting for years or even decades. Volcano's long-term eruptive activity dates back to the 1930s. Reventador's current activity has persisted since 2008. Sheveluch has had long-lived activity since the late 1990s. Great Sitkin has been in eruption since 2021. Kīlauea's current summit episode began in 2024. When all of those are plotted as red icons beside genuinely new episodes, the map visually compresses very different histories into one moment. The result can look like simultaneous awakening, even though many systems never went to sleep. There is also an information cycle effect. When one spectacular eruption goes viral, people begin noticing every other volcano report. Recommendation algorithms then deliver more volcano videos, more ash cloud clips, more seismic maps, and more dramatic headlines. A person who normally sees one volcanic story a month can suddenly see 10 in a day. That change is real in the media environment, but it is not necessarily real in the mantle. Human attention clusters just as strongly as natural events do. Scientists guard against that bias by using long data sets and standardized definitions. An eruption start date, an eruption end date, an alert level change, a seismic swarm, and an ash advisory are not interchangeable events. The weekly volcanic activity report also states that it is not comprehensive. It summarizes selected activity that meets reporting criteria. Therefore, a higher number of entries in 1 week cannot by itself establish a physical increase in worldwide volcanism. To claim a global spike, researchers would need a sustained statistical change after correcting for monitoring coverage, reporting practices, and the number of long-lived ongoing eruptions. So what would genuine evidence of a global change look like? We'd want to see multiple independent data sets moving in the same direction over a meaningful period. the number of new eruptions would rise above the expected historical distribution. Eruption magnitude might shift. Regions with very different tectonic settings would show synchronized changes that cannot be explained by local processes. The effect would persist after accounting for new satellites, new observatories, and improved reporting. There would be a physical mechanism capable of producing the pattern. At the moment, that case has not been made. What scientists do see is a restless planet operating normally. Plates continue to move by centimeters per year. Subduction zones continue to recycle oceanic crust. Mantle melts continue to rise. Volcanoes inflate and deflate. Magma stalls, crystallizes, mixes, and sometimes erects. Hydrothermal systems boil and fracture rock. Earthquakes alter stresses locally. Some weeks bring several spectacular events. Others are dominated by slow lava flows and low-level ash emissions that barely make international news. This is not a static planet becoming active. It is an active planet becoming more visible. That visibility is a major public safety advantage. Satellite thermal sensors can detect hot lava at remote volcanoes. Radar can measure deformation through clouds. Seismic stations stream data in real time. Gas instruments can identify changes in degassing. Aviation centers issue ash advisories within minutes. Mobile alerts reach communities near danger zones. The same technology that makes the world seem more volcanically chaotic also gives people more warning than previous generations had. But better warning does not remove uncertainty. Volcanic systems are complex and nonlinear. A volcano can show escalating unrest and then settle down. Another can move rapidly from moderate unrest to eruption. Some phreatic explosions are driven by steam and can occur with limited warning. Eruption forecasting is strongest when scientists can compare multiple signals with a well-documented history of the same volcano. That is why local observatories are more useful than global viral maps when deciding whether a specific community is in danger. For people near active volcanoes, the practical message is simple. Follow the official observatory responsible for your volcano. Know the current alert level and what that level means locally, because alert systems differ between countries. Respect permanent danger zones. If ashfall is possible, protect water supplies, keep masks and eye protection available, and avoid driving unless necessary, because ash can reduce visibility and damage engines. If authorities warn about lahars, stay away from river valleys and channels. If evacuation is ordered, move early rather than waiting to see lava or ash with your own eyes. For travelers in aviation, the risk can be very different. A volcano may pose little danger to distant communities while generating an ash cloud capable of disrupting major flight routes. Kamchatka and the Aleutian Islands are remote, but their volcanoes sit beneath busy trans-Pacific air corridors. Indonesia and Japan also lie beneath heavily traveled routes. That is why aviation color codes and volcanic ash advisory centers are a critical part of global monitoring. A short explosive pulse can become an international transportation issue, even when the eruption itself remains geographically small. So is volcanic unrest spiking worldwide? The most accurate answer on August 12, 2026, is that several notable volcanic systems are active or changing at the same time, and the latest completed Smithsonian USGS weekly report was busier than its long-term reporting average. But the global statistics do not show evidence of a sustained worldwide increase in volcanism. Many of the volcanoes now in headlines are part of long-running eruptions. Others are showing local unrest inside regions where multiple active systems are expected. Is real. A planetary volcanic awakening is not supported by the evidence. And is it coincidence or something more? It is more than random in one important sense. Volcanoes cluster geographically because plate tectonics concentrates them along subduction zones, spreading centers, rifts, and hotspots. Regional earthquakes can sometimes perturb nearby volcanoes. Shared tectonic environments can create periods when several systems in one region are restless. But there is no evidence that Etna, Kīlauea, Mayon, Sheveluch, Reventador, and Indonesia's volcanic arcs are being driven by one synchronized global pulse. Their overlap in time is better explained by the high normal background rate of volcanism, natural clustering, and modern monitoring. The next few weeks will still be worth watching closely. Kīlauea's summit may begin another fountaining episode if the current recharge pattern continues. Mayon remains of background even after its alert level was lowered. Sinabung's renewed seismicity deserves continued observation. Sheveluch, Reventador, Merapi, Semeru, Ibu, Dukono, and other long-running systems can produce hazardous changes with little interest from the wider world until a plume becomes large. None of those possibilities require a global trigger to be serious. The deeper lesson is that the Earth does not need to be entering a new volcanic era to create dangerous eruptions. Normal volcanism is already powerful. A single local escalation can threaten towns, close airspace, bury crops in ash, trigger lahars, or force evacuations. The right response to a dramatic global map is not panic and not dismissal. It is to ask which volcanoes are actually changing, what their monitoring data show, and whether local authorities are raising or lowering their assessments. So when you see 10 volcanic headlines stacked together, remember the baseline. Earth usually has dozens of continuing eruptions. Around 20 volcanoes may be erupting on a given day. The Ring of Fire contains hundreds of Holocene volcanoes. Modern satellites can reveal events that earlier generations would never have known about in real time. Busy weeks will happen. Some will include spectacular ash plumes and lava fountains. The scientific challenge is to distinguish a cluster from a trend. Right now, the data favor cluster, not trend. The planet is restless because it has always been restless on human timescales. What has changed most dramatically is our ability to watch it. If that conclusion changes, the evidence will not come from one viral montage. It will come from long-term eruption statistics, observatory networks, deformation measurements, seismic records, gas data, and peer-reviewed analysis showing that the background itself has shifted. Until then, every volcano should be judged on its own signals and its own hazards. Tell me in the comments which volcano you want us to track next. Kīlauea, Etna, Mayon, Sheveluch, Yellowstone, or another system. And if this breakdown helps separate real geological warning signs from the global awakening narrative, hit the like button and subscribe. We will keep following the official observatories, the satellite data, and the eruption reports as conditions change. No panic, no dismissal, just the evidence and the full picture. See you in the next one.